Good morning. I hope you had a lovely Thanksgiving. I did too. I just enjoyed the days off tremendously. I did a lot of reading, which is my favorite hobby. All right. Well, we're going to start talking now about the particle model of matter. Now that we've done density and mass at the level of measurement, it's good to be talking about what does that mean in new contexts. And so you're going to be particularly able to do that. And I think you'll be impressed at your knowledge. All right, so this is called the particle model of matter, atomic and compound particles. All right, so atomic particles are atoms. All right, we'll just make an atom. Whereas a compound particle, let's just do water because it's the most common. All right, with oxygen and then hydrogen. I'll show different ones by having them either open, outlined but open, or full. All right, so then this whole thing would be a particle, and it would have a little bit odd shape, where atoms are spherical, but of different sizes. Matter's mass and volume can be measured, but we've been doing that. What is matter made of? What makes copper different from iron? What makes water different from gasoline? And how do we know if matter is pure or not? All right, so those are the things that we're going to weave mass and volume into. The evidence of particles at the smallest level of matter. There is plenty of evidence that matter is made of tiny particles like grains of sand, only much, much tinier. We're calling them particles, even though there are atoms, atomic particles, which we call atoms, and compound particles. I'm going to abbreviate them CMPD for compound particles like water, because they have two or more different kinds of atoms. So water, this is hydrogen, right? And hydrogen. And then this guy is oxygen, and the formula for water, as we know, is H2O. And the formula tells us what's in the particle. All right, so here is our particle right here. All right, and it's all stuck together. There are 118 elemental particles and millions of compound particles. Let's just look at the 118 that we know. All right, so we're pretty familiar with this after our astronomy unit, where we found these were created in the stars, and then the largest ones in supernova explosions. So the most common ones are these that are on the top, correct? Yeah, so the most common are hydrogen and helium. All right, most common. We know that from astronomy. They were created in, hydrogen was created in the Big Bang, and helium not long after that. So then we go down and we see that there's 118 of these elements, but many of them are not very familiar to us. All right, the ones that are most familiar to us are the metals, which are across here. These are called the transition metal elements. All right, and many of the ones we know, like copper, iron, zinc, silver, gold, platinum, are in this transition metal area. All right, and then we get down to these guys who actually fit in right here and make the periodic table much wider. All right, we know these are all radioactive. After number 53, they're all radioactive. All right, so these are all radioactive. And so are these radioactive. All right, so we're not going to be studying nuclear chemistry. In this unit, we're going to be studying chemistry of the elements that are not radioactive. So that's going to be focusing really on common chemical reactions that occur on the earth. All right? And the common ones that surround us in day-to-day activities. All right, so we have all the elements we're familiar with. These are the alkali metals you'll get more familiar with. These are the noble gases, which you've heard of before. All right, and then here's, of course, carbon and nitrogen and oxygen. These two are the components of air. Okay, so there's plenty of evidence that matter is made of tiny particles like grains of sand, but much, much smaller. We're calling them particles. And there's two kinds of particles that are important to us, atomic and compound particles. But there's also a third kind, which we discovered in plasma, ionic particles. That is, they have either an extra couple of electrons or they've lost a few electrons. So they have a plus or a negative charge. All right, those are the three kinds of particles that we are talking about here. All right, so fact, the periodic table shows 118 different kinds of atomic particles called atoms. Another fact is we all know food burns, so I wanted to pick one that you're all very aware of. It turns black, right, when you burn it? And that's because all food, plant, and animal matter is made of compounds containing carbon. The black color of charcoal shows carbon atoms. All right, so when you see charcoal, and you maybe hadn't thought of what's on the outside of the food as charcoal, but that's what it is. The rest of the substances that were in the food are in the gas state of matter after burning, usually. All right, so fact, carbon is a black solid, and compounds containing carbon are called molecules. There are millions of these, and they are what we live off. Plant and animal matter are made of carbon-containing compounds. Millions of these. And we just call these molecules, all right? They're different than molecules, or that, I should say they're different from compounds that are more like rocks. All right, the third idea I want to talk about is that matter is made of tiny particles, and that means they're separate, minuscule, tiny particles with some space in between them. So if you look at the sand at the beach, for example, with a magnifying glass, you'll see more than one kind of granule. You'll see that beach sand is a mixture of particles of different kinds. So usually you see the lighter particles of sand, and then maybe you see black sand in there that's usually iron, because there's plenty of iron in the rocks, all right, on land. All right, and then iron has this peculiar property that it's sensitive to magnets, and that's a separate property of iron. I believe you already know that as well. So, another fact, matter is made of separate, minuscule particles with some space between them. And the space is empty. The space is empty. Well, how small are we talking about? This is difficult for us because we don't really think this way, do we? So let me just spread this out a bit. All right, so here we have, there I am, right there, a human being. All right, so we are at meter amounts. So I'm about 2 meters tall. You're about 2 meters tall. All right, so we're about 2 meters tall. All right, and then you can see that we're moving to into the body, into cells. All right, into the body. So these are large nerve cells, and you've probably seen pictures of those before. They look like stars. All right, and then we see the size of a chicken egg. Eggs, chicken egg. We know the dimensions of a chicken egg. And then we get to frog eggs. Oh, you know, stuff that's really small. versus chicken eggs. All right, so frog eggs. All right, now let's just think about what we have so far. So the point that this is making is that if you can see it with the unaided eye, we call this macroscopic. Macro meaning big. Scope means vision. All right. So macroscopic is the word that we use to describe the, okay, is what we use to describe anything that we can see, feel, touch, sense, etc. All right. Now here it has, we had things going up then to 10 meters, 1 meter. So humans are at the early end of this. All right. And then the length of some of these nerve cells are between 1/10 of a meter. All right, 1/10 of a meter. And then 100th of a meter. So when we're getting to eggs, we're talking about things that are between 0 and 10 centimeters. All right, a centimeter is 2.5 inches. A centimeter is, no, that's not right. There's 2.5 centimeters in an inch. 2.5 centimeters. Centimeters in 1 inch. All right, so that's a centimeters. All right, so we're talking about 1 centimeter here, so you can picture that on the rulers, can't you, about how wide that is? All right, up to 1/10 of a meter, which is 100 centimeters, right? All right, 1 centimeter. All right, and then we get to frogs' eggs, and we're starting to get to the point where we have trouble seeing them. We would probably need a microscope, a magnifying glass to see this. So this is maybe magnifying glass territory. Magnifying. All right. Now, suddenly we're at the end of what we can see. So until a microscope was invented, which was in the 1600s, people could see that there were pepper grains, etc., and little grains of dust in the light, but they couldn't really see anything with any definition whatsoever. It just looked like a small speck. All right, with the invention of the microscope, a whole new world opened up. They began to put samples of pond water on there and see all these organisms. They looked at all sorts of types of samples, from the food that they were eating to the water they were drinking, and finding all kinds of little wiggly things. So that was the invention, or the belief, that there was a new world down there, and it's a new world, and primarily a bacterial world. Can you imagine what it was like to find that there was all that bacteria? That there were all those wiggly things in the water that they drank and the food that they ate. Now, they're still in our water, aren't they? To some degree. And they're still in our environment, aren't they? To some degree. In fact, apparently we're covered with bacteria. Yeah. And that they kind of insulate us in a way and are part of our ecosystem. So humans are an ecosystem for bacteria. Kind of interesting. All right. But then we get to plant and animal cells. So I think onion skins were one of the first things they put under. They have such gigantic cells. And then they began looking at smaller and smaller things and began to see plant and animal cells of a whole variety of sizes. All right. So now we are at, oh, well, size-wise, we're down here at 10 to the minus third meter. 10 to the minus 6 meters, 10 to, all right, I'm sorry, I'm doing that. Let me do this a little bit better. All right, so let me find a micrometer. All right, here we are at 10 to the minus 6 meters. So as we go up in size, now we have 10 of those micrometers, and then 100 micrometers, and then 1 millimeter, which we know is that tiniest little mark on the ruler on the cells on the metric side, that tiniest of little marking, and that is the millimeter. So it's like the distance when you put your fingernails together. It's kind of like that tiny little distance. All right, so amazing. A whole new world opened up, that especially of classifications of now of animals that couldn't have been seen before, bacteria, algae, and of course viruses had not been yet discovered. So look at the area, we're going deeper and deeper. So we're now at 10 to the minus 6th meter. All right. Now we're getting to very tiny bacteria. Tiny bacteria. But the category we're in is 10 to the minus 9th meter. That is 000 meter. All right. Now let's see what we get at 10 of those nanometers, they're called. There's ribosomes, and a little bigger than that are some of the viruses. So now we can see how the light microscope stops here? Hundreds of years go by, and there are improvements in microscopes. They work on the lenses, and you know how high power became about, so it's 10 times the traditional power of a microscope. But it wasn't until the 20th century that something new was developed called the electron microscope. So instead of a beam of light, there's a beam of electrons that are allowing us to see what's under the microscope. The light hitting objects is reflected back and we get an image. The electron beam hitting the object is reflected back and we get an image. All right, now suddenly, for the very first time in the 1900s, we began to see viruses which we didn't know existed. The tobacco mosaic virus was, I think, the first one. So we had hundreds of years to study bacteria, but you can see why viruses have been such a problem for medical science, because they've only recently been discovered, and we're seeming to discover more and more new kinds, partly because they are evolving, or as we know now, mutating from one to the other over time. All right. So we went from the microscope to be able to see bacteria, big bacteria, plant and animal cells, most bacteria then, and then mitochondria in the cells, you know, the power plants of the cell. And then to the smallest bacteria, once the electron microscope was invented, then we could see smaller bacteria. And then viruses, which are unlike bacteria because they're just scraps or pieces of RNA or DNA that are really not viable outside themselves. They have to have a host. Bacteria can live on their own, but viruses cannot. And then we're here to ribosomes, all right, in the cells. And then at 10 nanometers, we start getting to very large molecules. Here we could see DNA, because DNA is an enormous molecule. These are considerably smaller, but they're much, much bigger than most we will deal with, most of the chemicals we will deal with, proteins and lipids. So now we're starting to see small molecules like the kind that we have on our walls. All right, that the formulas are on the walls, the structural formulas. So small molecules begin to show at 10 to the minus nanometers. And now we're at 10 to the minus 9. And this is 10 to the minus 10th meter. We begin to see atoms. So this is what we call the atomic level of matter. The microscopic level of matter, what we can see under the microscope. The atomic level of matter is where atoms and molecules live. So basically all the kinds of little particles that we're talking about. Lipids are a large particle made of many atoms, as are proteins, very, very large, made up of many, many atoms. All right, and down here we're getting to talk about individual atoms, All right, so one of the things that I'm trying to do is help you to get yourself to think that life doesn't just exist at the things we can see, but that life exists at the microscopic level, as probably you began to think about in 7th and 8th grade. And then next year in bio, you'll think about it a whole lot more. And then now we're talking about what's even lower than that in terms of size. And we get to the point we need a scanning, tunneling microscope. Scanning, tunneling microscope. All right. This was invented. I'm going to go out on a limb and say 1970s. But you know, when things are invented, that takes decades before we have a lot of data from them. All right. So this allows you to see atoms lined up. So in the same way, it's not reflecting light. It's not reflecting electrons. This has a different mechanism, but it's the same concept of a probe going in, and by what the probe hits and the height at which it hits, that is translated by the computer into an image. All right, into an image. All right, so at the basic idea of size. All right, so this is called size or magnitude of matter. So any sample large enough for us to see down here must be made of huge numbers of particles. Huge numbers, millions, billions, trillions of particles. All right. Now, What are we to say about the particles at the atomic level of matter? Well, all matter is made of atoms, the smallest atomic level particle. Let's go over here. I wrote this note for you since we've studied nuclear chemistry, that protons, electrons, neutrons, and quarks are smaller. But the reason that they are not considered to be the basic particle of matter is they are not an identifiable element. They simply are components of an element that can be mixed in many different ways. All right. It's the atoms themselves that are the ones that are identifiable as particular pieces of matter and not just building blocks. All right. Now, all matter is made of atoms. Yes, you knew that, I betcha. The periodic table shows that there's 118 kinds. We knew that. As you know, each element has a symbol shown on the periodic table. We knew that, didn't we? Yeah, let's go over here and look. I have another one. Each of the elements has a symbol. It's either one letter, like phosphorus here, sulfur, or it's two letters, like copper, zinc, etc. And there are a few right here that don't have any name. These may have names by now. But remember what I said about the reason that we're not as interested in these as you might expect is because they don't last very long. They've been made in the laboratory, so they're pretty unuseful right now. They simply have been made. All right, they don't have a function yet for us. Whereas the other elements, these more common elements, are an everyday component of everything that we are around. All right, so each element has a symbol, and the symbol is the chemical formula. So the chemical formula for copper, it's one of my favorite elements, is Cu. It comes from the Latin name. Excuse me. Atoms are spherical particles. Three-dimensional circle is called a sphere, right? Different kinds of atoms have different masses. Oh, we've kind of talked about that before. Atoms in a row across from left to right have more mass. So if we go this direction, we get to more mass. All right, as you go from that way. As you go down, you get more mass, more massive, more mass. All right. So, and we had talked about the fact that these biggest elements are rarer. All right, the smaller atoms are more common, are more abundant. Let's see. Atoms are electrically neutral. We've talked about that. Same number of positive charges, like let's say 3 positive and 3 negative. All right. And when you add up positive 3 and negative 3, you get 0, right? And that's what neutral means. All right. Plasma has ions because the electrons have been ripped off matter. So the negative charges come from the electrons, and the positive charges come from the protons in the nucleus. And then remember, neutrons don't have any charge. All right, so let's see. We have some questions here. Which atom shown on the periodic table has the smallest mass, and how do you know? All right, so go ahead. You may talk with your partner about this. What I'll probably do right now is make this a bit larger because they're so small. Yeah, these are a little small. Let me make them a size 20. All right, and then spread them out here. Let's make them bold even, and that will help us. Now, you have this side by side on your piece of paper, right? So that's the other reason why I like to broadcast to you, because some of the sizes of the print is too small for you to see. All right, so which atom shown on the periodic table has the smallest mass, and how do you know? Well, based on what we said, it should be at the top, right? And it should be over here on this side, because you get more mass going this direction, correct? All right, and they get more massive going down, so this guy should be the smallest. And who is it? Oh, it's hydrogen. Yes, hydrogen. So we would say hydrogen is smallest it's the top left, and top left element should be the lightest, just based on those trends, right? Top left element should be the lightest. And then let's go look and see if we can see if there's any other information. So I'm going to make this gigantic, and when I do, oh, well, you can't see real well, but this says 1.008 is the mass, the average mass of all the hydrogen atoms, and helium, O is 4.00 is the average mass of the helium atoms. So that is another way to prove. All right, that's another way to prove that that hydrogen is. Hydrogen's, I'm going to use its symbol. Hydrogen's mass is average mass. Average mass is 1.008. The next smallest is 4. Smallest is 4. So do you see how I'm trying to help you learn how to get information from sources? You know, whether it's from graphs, whether it's from tables. Which atom has the largest mass, and how do you know? Well, we know who to suspect, don't we? Let's go see. We know who to suspect because I have it below here as well as up there. Let me get it. Where are you? There. Let's see. We kind of expect it to be this guy, right? But he has an unknown mass. So these guys are pretty unknown. And you see how we still don't know very much about these, but they appear to be in the 273 range. Uranium is 235 about. All right, so it looks like the largest one, we would expect it to be this guy, because he's at the bottom, right, where the biggest guys, the most massive guys, most massive meaning having the most mass. Even though we don't know for sure what it is, because scientists have not determined it, or at least we didn't know when this table was published, and I don't know either. Okay, but this is the one we would suspect to be the most massive. All right, let's see. So we pick number 118. Okay, because the largest element should be on the bottom right. The largest, most massive element should be on the bottom following our trends. It doesn't mean has the biggest volume, but it means it's the most massive element. Should be on the bottom. So scientists look a lot at trends, so it should be on the bottom right, just like hydrogen was at the top left. All right, that's how we know. What kind of atom do you know that responds to a magnet? Go ahead and write that down. What kind of atom is a part of all our carbohydrates, fats, and proteins that we and all the other living organisms eat? What kind of atom is a part of all of that? That is a very interesting fact. Some facts are just facts. The answer to this is a very interesting fact. So talk it over with your partners. What element is the element of life? What element is in all our food? What element fills our body? All right, now copper is different. So right here, this doesn't stand out as much as it should because this is kind of important. Copper is different from silver. How? Well, it's different in its properties. We know copper is that beautiful orange color, and silver is beautiful silver. However, they're both shiny, right? Shininess is a property as well. Copper is different from silver in many of its properties because copper is made of copper atoms, whereas silver is made of silver atoms. So if I ask you what copper's made of, it's made of copper atoms. If I ask you what gold is made of, you'd say gold atoms. If I ask you what uranium is made of, you would say, well, uranium atoms. So if I asked you any element on the periodic table, you would know that it was made of its own kind of atom. So fact, all the elements differ in properties because each is made of its own kind of atom. Yes, 118 different kinds. Now, water is different in its properties because water is made of H2O particles and gasoline is made of C8H18 particles. These chemical formulas, H2O and C8H8, show which atoms are glued together in this compound and how many of each kind are present. So the formula H2O that we just know tells us that there are two hydrogens. This little subscript after hydrogens, it says there's two hydrogen atoms and one oxygen atom glued together to form a water particle. In contrast, gasoline is made of, it's a mixture, but its primary component is C8H18, which means it has 8 carbon atoms bonded to 18 hydrogen atoms. They're bonded together and it forms one particle. These chemical formulas show which atoms are glued together in the compound and how many of each kind are present. Now we're going to make the same sort of statement. Different chemical compounds are different in their properties because each compound is made of entirely its own kind of particle. So water, pure water, is made only of water particles. Pure gasoline is only made of the C8H18 octane particles. All right. Now, let's pick up density, which we've been doing. The density of a substance depends on the number and mass of the particles that are in it, and the amount of volume these particles take up. And of course, we know that density equals mass divided by the volume. All right? So, the mass of each particle depends on which atoms are in it. So we saw that there are masses on the bottom of each square that indicate how much an average atom of each element, how massive, I should say, each element is, or how small it is. All right, and how many of each kinds there are. So that would give you the mass. It's the mass of all the atoms that are present, plus then that's the mass of the particle. All right, so the number and mass of the particles. So now we may have 1,000,000 of those particles, and so 1,000,000 times the mass of one particle. Then the volume depends on how the particles, these 1,000,000 particles, are attracted to each other and fit together. Atoms are spherical, right? Whereas compounds are irregular shapes, just like I showed you water, H2O. Those aren't. Each atom is a sphere, but the particle itself, when it's glued together, isn't spherical. And the state of matter changes the arrangement of particles, as we saw. That particles are really close together in a solid, all right, and move farther away in a liquid. Now, fact, the densities of metallic elements in the periodic table can vary amazingly. Most of the elements in the periodic table are metals. Okay, most of them are. So here is the density of some common metals. All right, so the metal and the density in grams per centimeters cubed, and we know that's the same thing as saying grams per milliliter. All right, so I gave you, I think there's about 16 elements here, and it gives a range, so you can see the range of these goes from very small. Well, here's one that's 1, and oh, here's one that's 21. Don't know if there's anybody bigger than that. All right, so what must be true about the particles' mass and arrangement in aluminum compared to those in gold? Let's see, aluminum. Gold. Gold, 19.3. Oh my goodness. Well, the first thing, let's just say this is close to 3, almost 3. All right, so the density's about 7 times higher. Yeah. In fact, let's just figure that out because we can do that with no problem. Let's go here. All right, so let's have 19.3 and divide by 2.71 and see how much bigger that is. Okay, 7 times bigger. All right, so the density of gold is 7 times more than aluminum. So based on this density chart, all right, what must be true about the particles' mass and arrangement in aluminum compared to those in gold? Well, the two key factors were the size of the atoms and the number of atoms and the space they take up. All right, so when we look on the periodic table just to see where these are located, we find aluminum is way up here, number 13. And these have a mass of 20, almost 27, And then gold right here has a mass of 190 something. I can't read it. 190 versus 27. Oh my gosh. The mass let's do a Control Z to get that out of the way. All right, you go where you're supposed to be. All right. Let's see if we accomplished our... Yes. Okay, so the density of gold is 7 times 4. The mass of aluminum is 27 about. The mass of gold is... Let's just go look up average mass of gold since I can't read it. Average mass of gold atoms. Yeah, but we want to know. But we want to know in grams. 197. Okay. Is 197. So 197 to 27. How much bigger is that? 197. Do you see how I'm just using ratios? Now I'm doing the ratio of mass. Oh, 7.29. It's also about 7 times more in gold. All right. So now we're left, well, what must be true about the particles' mass and arrangement in aluminum compared to those of gold? Well, we have our data. All right, so here's our data. All right, we collected some data. Now we have to say, well, it looks like the gold atom is so much bigger. Is responsible, the gold atom's, mass is responsible for the difference in density. All right, rather than the particle arrangement. The particle arrangement is probably pretty similar in both of them, since the density difference is 7-fold, and so is the mass difference. All right, so probably different densities, it's not due to the differing particle arrangement. Yeah, that would create a different volume, right? Wouldn't they? All right. Now, what I want you to do is create a table here based on the information I gave you. I want you to take this and I want you to put the metal and its symbol, give the density from the table over here, but I want the order to be from the lowest density to the highest. So now I want you to get familiar with the densities. You could tell by how I act when I saw your results that I could tell what the metal was from its density, or I had a good idea who it was. And that's what I'm trying for you to do, is get familiar with metals based on their density. So finish this right now, please. And then we will be done for the day. So remember, when we have a video, I'm expecting you to have taken all the notes on your own sheet because you have my screen and your screen side by side. Last thing I'll check is whether you finished this table. All right, and I'll want to know that. So show me that you're willing to think. I'll talk to you soon. Bye.